We want to look at some counting techniques to help us solve harder probability questions in the Extension 1 course. So we call these counting techniques permutations and combinations. Now, one of the first things we want to do though is look at some other counting techniques, like simple counting techniques, which are pretty much logical, but it helps build into the permutations that we want to do here. So the first thing we want to do is have a look at the idea of if you can have a number of events happening and combining. So if the first one can happen in X ways and the second one can happen in Y ways, then all up the two events you can have X times Y different ways of doing things. So for example, if you've got 3 boys and 5 girls in a class, how many boy-girl combinations could you have? So for every boy, you could pick 5 girls, and vice versa. For every girl, you could pick 3 boys to partner there. So you could have 15 ways all up. So this is what we just call a simple counting technique. So if we had 2-digit numbers being formed by these digits, so 1, 2, 3, 4, 5, then you could have how many 2-digit numbers? If there's no repeats, if repeats are allowed, so we'd have 25 different numbers we could form. 2-digit numbers we could form with those 5 digits, because you get 5 in the first and 5 could be in the second. In this one we got the same idea, but if no repetition of digits are allowed, we have 5 that can be in the first digit, but then they can't be repeated, so we've only got 4 to choose from for the second digit. So it gives us 20 all up. So we're looking at an idea of an 8-digit telephone numbers being formed from 0 to 9. If 0 can't be used as the first digit, well, we've got the idea that we've only got 9 to choose from the first, but then any digit can be used and repeated as you go through. So a simple way to write that would be 9 times 10 to the power of 7. This time we've got in a restaurant, we've got a menu with 5 entrees, 8 main courses and 4 desserts, which you can choose from. How many combinations could you get? Well, the 5 entrees could have any one of 8 dessert main courses, which could have any one of 4 desserts. So we do our multiplication. There's 160 different combinations that we could have there. Now, let's have a look at the idea of a permutation. Now, again, permutation is just an idea of counting techniques. Really, we had a little bit of a combination in a permutation in our counting techniques just then. But the idea of a permutation is that you're selecting a certain amount of objects from a whole group. So the idea that if we had 27 people in a class, and I just wanted to pick 3 people, how many ways could I pick 3 people? Well, the first person I could choose from, I'd have 27 options. And obviously, I can't pick the same person again. So for the second person, I'd have 26 options. And the third person, I'd have 25 options. So I could write that as 27 times 26 times 25. The other way to think about this is using what we call our permutation notation and the NPR. Now, we saw the NCR notation in the work we did on the binomial theorem. And we saw how that was able to use. So the idea of NPR being n factorial over n minus r factorial shouldn't be too new to us. We know what a factorial is. So the idea though here is that permutation is what we've just done here. How many ways can I pick groups of 3 in a particular order? So the idea that with a permutation we have an order that needs to be adhered to. That's really important. A combination we dealt with the NCR notation order doesn't matter. So, and we can talk about that a little bit later on. But the idea that permutation is an ordered set. So the idea here we say 27p3, which would be 27 factorial over 27 minus 3 factorial, or 27 factorial over 24 factorial, which means that if we wrote 27 factorial as 27 times 26 times 25 times 24 factorial, the 24 factorials cancel, leaves us with that 27 times 26 times 25 that we were talking about there. So that's basically, we can write we can do it either way. We can write it that way, or we can use an idea of a permutation and put it in our calculator. Again, our calculators bypass these steps for us and bring us down straight to our answer. But this is what a permutation is talking about: an ordered set of objects that we're choosing from a whole set. So this time we've got a class containing 15 pupils. How many ways can we find the first, second, and third prizes being awarded? So as we said in previous discussion, we could write that, well, 15 people could get first, and then 14 people would be left to get second, and then once we've chosen 13 people, we're left to get third, which gives us 2,730. Or you could put it in calculator as 15p3. How many ways can we get? 3 ordered groups from 15. And then if we've got Joanne wanting to win a prize, well, the idea here is that Joanne will either take first, second, or third. So we could write that as 14p2, which means Joanne's got to have one prize. The other 2 prizes have to go to 2 other people in the class. So how many ways could we get 2 people from the other 14? And because Joanne could be one of 3 different positions, so either first, second, or third, then we multiply that by 3, because that would only give us, if Joanne got first, for example, the other 2 could be picked in 14p2 ways. So doing that calculation comes down to 546. The other way to look at it over here is the idea: if Joanne gets first, as we said, then somebody would have to get second, and then another person would have to get third. Or if Joanne can't get first, there's only 14 people to get first, Joanne gets second, and then there's one of 13 people who become third. Or if Joanne has to get third, well, 14 people would get first, and then 13 people would get second. Do that calculation, it comes up with the same number. So there's different ways to calculate it and think about it, but it comes out the same way. If we have prizes in English, maths, and history, and could be awarded in all 15 of these subjects, well, how can we do that? Well, that would be the 15p3, because for each subject you'd have 3 different ways of selecting. We want three selections out of 15 in order, and then we could do that from English, maths, and science. Well, we cube it, and it's going to become a lot of different ways we can do that. So in horse racing, this is how we start to get your ideas of how much it will cost you to put a bet on and things like that. Because if you wanted to get a trifecta, for example, in a Melbourne Cup with 24 horses, how many ways can first, second, and third take place? Well, you've got 24 horses in the race, and they have to finish in a particular order, because they have to take first, second, and third. So 24p3 gives us 12,144. So if you wanted to place a bet on every combination or every permutation, really, to make sure you take out the trifecta in the Melbourne Cup, it's going to cost you $12,144. So it's not a cheap exercise. You won't probably get your money back. In this one, we've got, again, to think of these logically. So you've got to read and maybe do diagrams like I've done here and see how this comes about. So we've got judges that have put 7 candidates in an order of merit. So you've got 7 different people wanting to put them in order. So there's the key. It's a permutation. How many different orders are there? If we're going to put X next to Y, well, let's think about it. If X has to go next to Y, really we could consider them as one unit, because they've got to be together every time. So they could be in this spot, or they could be in the next spot, and one person would be in front of them. So anyway, if we consider it as one unit, and then we'd have 1, 2, 3, 4, 5, 6 units altogether, and they can be lined up with those other people in six factorial ways. Because there's 6 factorial ways that they could be. They could be in the first one. There's 6 to choose in the first spot, 5 to choose in the second, 3, 4 to spot in the second, in the third, and so on down to 1. But then the idea that, well, it just says X has to be next to Y. So the order for X and Y could be Y times X, as long as they're together, and then you could repeat the same thing. So there's what we've got to consider is that if we consider them as one unit, then they can be ordered 6 factorial ways. So instead of 7 candidates, we'd consider 6 candidates, with 2 of them being together. But then x and y can be ordered in 2 factorial ways, which is the same as 2. So that's how we can calculate that x has to be next to y. Consider them as one unit, but then in that unit together, how many ways can they be ordered? So what about with x above y? So as long as x is in that spot, in the first spot, y could be any other spots. And if x is in the second spot, then y has to be in the other 5. If x is in the third spot, y would have to be in the 4. And all the way through to the second last spot, because x can't be in the last spot, because if x has to be above y. As such there. So, if we look at it that way, and we can count them up and get half of the 7 factorial. But if we consider 7 candidates could be in 7 factorial ways. So if you've got 7 candidates, they can be put into a line 7 factorial ways. But if x is going to be in front of y in some ways, then y would have to be in front of x in other ways. So how many ways could be? Either x is above y or y is above x, which means it's going to happen half the time. Half the time x is going to be above y, but the other half, y is going to be above x. So we can consider it that way, and that's the easy way to consider it, rather than trying to write them out and count them and do all those different ways. So half of the 7 factorial would be 2,520. So that's a little bit of a tricky one, but one to consider, that x can be above y, but also y could be above x. And because it's only the 2 of them, it's going to happen half the time for x and the other half of the time for y. So half of the 7 factorial. So there's a few of the counting techniques to start off with, and that's what we're going to be concentrating on in this topic. And we're going to look at the next videos. We'll start to continue through the notes and look at some other type of problems that we can consider. But really, when you do the problems, you've got to start thinking logically about them and thinking about, well, where can certain spots be? Do I have to combine different units together? Different is it going to be a permutations and combination, or is it just a simple counting technique? All these things are going to come into play, and the more practice you do, as usual, the better you will get at picking which one it needs to be.